It worked on your laptop, then it failed on the test server. Same code, same commit, different result. For years, software teams lived inside that nightmare. The phrase everyone hated and everyone said, "It works on my machine." Libraries drifted, operating system packages disagreed. One developer's Python was 3.9, production was 3.7. A missing system library turned a Friday deploy into a weekend incident. The stakes were simple and brutal. If you could not freeze the world around an application, you could not trust it anywhere else. This is the story of how Docker turned that chaos into a portable, isolated unit, and what had to be invented for a single command to make a web server answer on port 80. Before containers won the argument, there was another answer: the virtual machine. A virtual machine gives every application its own guest operating system, sitting on a hypervisor above the host. That isolation is real and heavy. Each guest carries a full kernel, full boot sequence, and a serious memory bill. Spinning up dozens of them feels like parking a fleet of trucks when you only needed bicycles. Docker's rival idea is OS-level virtualization. Containers share the host's kernel. They package the application code with its dependencies, but they do not haul an entire guest OS along for the ride. The result is lighter startups, higher density, and environments that stay consistent from a developer laptop to the cloud. Portability, consistency, scalability, efficiency. Those are not slogans. They are what you get when isolation stops requiring a second operating system. So how do you freeze an environment without freezing a whole machine? Docker's answer is a three-step chain. First, a Docker file, a plain text recipe written in a small domain-specific language. Instructions run from top to bottom. Base image, dependencies, copy the app, set the command that should start. When you build that file, the daemon assembles a Docker image, a layered read-only package that holds everything needed to run: code, runtime, libraries, environment variables, configuration. Then you run the image. That living process is the container. Dockerfile builds the image runs as the container, blueprint becomes instance, static becomes dynamic. That chain is the whole manufacturing line behind every container you will ever start. Here is the distinction that clears most of the confusion. A Docker image is the blueprint, static, read-only, made of stacked layers. It does not run by itself. It defines how a container should be created, which software, which configuration, which starting command. A Docker container is the live instance of that blueprint, lightweight, isolated, sharing the host kernel while behaving like its own little world. Multiple containers can sit on one machine without stepping on each other. When the image executes, you get the container. When the container stops, the blueprint is still there, ready to spawn another identical life. Think of a class and an object, or a shipping container and the ship that carries many of them. The image is reusable. The container is replaceable. Type a Docker command and it feels local, but the real work happens elsewhere. Docker is a client-server system. The Docker client, usually the command line, is your remote control. It turns words like Docker build, Docker pull, and Docker run into REST API requests. Those requests travel over a Unix socket or a network to the Docker daemon, often called Dockered. The daemon is the brain on the Docker host. It listens, it manages images, containers, networks, and volumes. It can even talk to other daemons in a multi-host cluster. The host itself is the machine, physical or virtual, that holds the operating system kernel, the daemon, the images you pulled, the containers you started, and the storage and network plumbing underneath. One client can speak to many daemons. One daemon quietly runs the show. But what if the image is not on your machine yet? That is where the registry enters the story. A Docker registry is a stateless, scalable store for images. The default public one is Docker Hub, a global warehouse where teams push images up and pull them down from anywhere on the internet. Official images for Ubuntu, Nginx, MySQL sit ready. Private registries, Harbor, cloud artifact stores keep proprietary images behind controlled doors. Commands make the lifecycle plain. Docker pull fetches. Docker push publishes. Docker login proves who you are. Public means shared standards. Private means organizational control. Either way, the registry turns a local blueprint into something the whole team or the whole world can reuse. Portability stops being a hope and becomes a download. Under the friendly CLI sits a deeper machine. The Docker engine is the runtime that makes containerization real. The client sends commands, the daemon receives them through the REST API. Below the daemon, containerd handles container lifecycle: start, stop, pause, delete. Shims keep daemonless containers tidy. And at the bottom, Runk talks to the Linux kernel. Runk is the low-level runtime. It creates the isolated namespaces and applies the resource controls. Without the engine chain, images stay files on disk. With it, a request becomes a running process bound to kernel primitives. Client to daemon to containerd to Runk to kernel. That relay is why one typed line can birth an isolated world. Containers are easy to replace, and that is also their trap. When a container runs, Docker adds a thin writable layer on top of the read-only image layers. Your process can write files, stop and remove the container, and that writable layer vanishes. Data gone. Like notes scribbled on a whiteboard that gets wiped when the meeting ends. So Docker offers escape hatches. Volumes, Docker-managed storage that outlives the container. Bind mounts, a direct path into a folder on the host. TMPFs mounts, memory-only space that disappears on stop but never touches the host disk. Choose wrong, and a restart erases the database you thought you saved. Choose right, and disposable compute can still hold durable state. The tension is permanent. Cattle, not pets, unless the data must survive. Isolation is not only about files. It is about who can talk to whom. Docker networking gives containers connectivity with different personalities. Bridge is the default private network on one host. Containers talk among themselves behind a virtual switch. Host mode shares the host's network stack directly. Less isolation, lower overhead. Overlay stitches containers across multiple hosts, the fabric of clusters. None means no external network. Mac VLAN gives a container its own MAC address on the physical network, as if it were a bare machine. Pick the driver for the story you are telling: safe sandbox, raw speed, multi-host mesh, or full disconnection. Networking is how a sealed box still joins the wider world on purpose. Now watch every piece fire in order. You type docker run -d -p80:80 nginx. 1. The client sends a REST request to the daemon. Create and run a container from the nginx image. 2. The daemon checks the host. Is nginx already local? 3. If not, it pulls from the registry. Docker Hub by default. 4. The daemon hands image and config to containerd. 5. Containerd calls Runk. Runk asks the Linux kernel for fresh namespaces and cgroup limits. 6. Execution. Docker maps host port 80 to container port 80. Inside the container's PID namespace, nginx becomes process number 1. From the outside, a web server answers. From the inside, a tiny isolated universe just booted. Because a relay race across client, daemon, registry, containerd, Runk, and kernel all finished cleanly. Efficiency has a shadow. Pack enough containers onto one kernel and they begin to compete. CPU cycles, memory pages, disk, and network I/O. Isolation of identity is not the same as isolation of appetite. Linux control groups, or Cgroups, are the answer Docker leans on. They limit how much CPU, memory, and I/O a container may consume. Namespaces hide the view. Cgroups hold the leash. Without those limits, a single runaway process can starve its neighbors. With them, density becomes safe enough for cloud-scale microservices. The quiz at the edge of the source material points here on purpose. The hard problem after packaging is governance. Who gets how much, and who enforces it when everything shares one kernel? So return to the opening stakes. The app that only worked on one laptop. Docker's reply was not another full operating system per service. It was a portable unit, a Docker file that freezes the recipe, an image that travels, a container that runs the same way on a laptop, a test box, or a production cluster. Client and daemon turn intent into action. Registries move blueprints across the internet. Runk and the kernel make isolation real. Volumes keep the data you cannot afford to lose. Cgroups keep the noisy neighbors in check. What became possible is repeatable deployment at the speed of a pull and a run. What remains open is the craft of operating that world at scale, balancing disposable compute with durable state, freedom with limits, speed with safety. The command is simple. The system underneath is a carefully negotiated piece. And every time a container answers on port 80, that piece holds, for now.